Okay. So let's see if I can put myself together here. Welcome to Discrete Math. I am Scott Grizzard from the University of South Florida. Look at that. I got a nameplate. There it is. The marketing people sent me the nameplate, but now my head is back at the top. Anyway, don't know why that's happening. Today we're going to be talking about counting, the rule of and the binomial theorem, and what that has to do with a deck of cards, and of course how to play poker. I've got the card cam set up. I'm very excited about this. See, check it out. The card cam is set up, so I can do card tricks on the thing. I loaned my other card cam to a TA who wanted to use it as a regular webcam, so I had to set up a new card cam. And then I accidentally erased everything. Of course there's gambling in class. No, there's not gambling in class. We are not gambling in class, okay? So it's a very important distinction, you know. A math professor, an economist, and a psychologist all go to Vegas. The economist says, I hate gambling because I'm risk averse. The psychologist says, I love gambling because it's a thrill. And the math professor says, what's gambling? So, you know. So, there you go. So again, today we're talking about list counting and let's see if this works. Yes. And the binomial theorem. Now you'll notice that my nice little outline is not complete because it all got erased. That was the technical difficulty I was having. Anyway, are there any questions before we begin? Again, so if you are in the Twitch chat, I am watching it. But remember that Twitch chat is not private. Anyone on the internet can see what you write on Twitch chat. If you want to ask questions more privately or just in the within the class, and you are in my class, you may do so on Discord. There is a Discord chat channel called 2020-08-27 Discrete Class, where everyone is complaining about PHP. Are there any questions, comments, issues, and stuff before I begin? Oh, and I do need to post where it is on Twitch chat on the screen, because I didn't do that, did I? Twitch TV Scott Grizzard. I need to post the link, don't I? Okay, so that's what we're talking about today. Yes, we will be covering the quiz. I'm getting to it right now. And then we will be doing some PHP today. We'll be looking at some PHP and how that connects to math. So that's going to be all sorts of exciting. I still don't have a TA. I am working on that project. Luckily, next week I will. I think he'll have everything set up for the other class. Also, we have another TA that's just joined the class, and we'll be introducing him next week. But he wasn't on the intro video because he's new. Well, I mean, he's not new. I just didn't think I'd get him as my TA. Will I be teaching you how to properly install and set up PHP? No, you were supposed to do that. So that's another thing. On Friday, I have a session specifically dedicated to going over issues with problem sets and coding issues. So that's what Friday is for. Now, it's like souped up office hours. You can either ask me questions in Discord. I will be happy to chat with you. I have a little video channel up, so it's more than just like the office hours where I only speak to you one-on-one. I'll actually have a room dedicated only to talking about code and PHP. So that's Friday. That's what the Friday sessions is about. And I'm on campus on Friday, as long as the weather is not raining. I'm going to have office hours set up outside. I'm going to be bringing a bunch of my mother's tailgating stuff, which is kind of exciting. I'll have a Bulls. Actually, I think she lost the Bulls canopy. I think it ripped. But I'll have a canopy of some sort, probably. I'll be in one of the parking lots, and I will announce where I am on campus in the announcements. So you can either talk to me over Discord, or you can actually come and talk to me in person. Bring your laptop, and we'll talk about it. Either way works for me. I'll have a big fan out there, so my audio won't be as good because I won't have my lovely microphone, but I will be there. Okay, so I think that's all the questions that people have asked. We're going over the quiz. Yes, we will be going over the quiz. Can we tailgate with the discrete math boys? No comment. So again, the class tomorrow, it's not really a class. It's sort of like office hours, but more. Okay? And it's dedicated to help with the problem sets, to only helping with the PHP coding. So during that class time, I'll be outside on campus. You can bring your laptop, or you can talk to me. I'll have my laptop with me, and it'll be open to Discord. And there'll be a special room on the Discord server for that. So it's not a lecture. It's completely optional to attend. But if you're having difficulty with the coding, or difficulty getting PHP installed, or difficulty in general with that aspect of the class, that is entirely dedicated to you. Yes, you can come by and get autographs. Bring your own autograph book, though, because I ran out of, math cards. Now, any other questions? Yes, Ubuntu, Linux, awful. No, Ubuntu's better. And no, we're not running it on other strange Linux type things. If you're coming in with your FreeSB and like, can I get PHP to work on that? I'm going to say yes, but that's your problem. There's a flame war going on in Discord chat about Linux being stinky, and not. So anyway, that's where they are. So yes, let's go over the quiz. Okay, so the quiz today. Are there any other questions? Okay. All right, so how many different messages can be encoding using 32 bits? And the answer there is 2 to the 32. Any questions about that one? So how do we feel about that? Oops, 5. What are we doing? Question 1. How do we feel about question 1 there, 1 to 5? Guys, if you want me to create a channel for you to have this Linux, Mac, Windows flame war in Discord, we will be putting. I'll create that I'll create a new channel for you. But let's try to keep it off the chat. Let's focus on the class stuff, if we would, please. At least a little bit, slightly more focus. All right. This next one. A equals 0, 1, 2, and 3. The set containing 0, 1, 2, 3. So what is the size of A? Well, it's 3. Now, what is 2 to the A? There was a question on number 1. Why is it 32 to the 32? Each bit doubles your number of messages you can encode. So with 1 bit, you can encode 2 messages. With 2 bits, 4. With 3 bits, 8, and so on and so on and so on. So it's 2 times 2 times 2 times 2 times 2 times 2 times 2, 32 times. And that gives you 2 to the 32. Okay, this symbol right here means the power set. So this question B is asking for the power set of A. Which is the set of all subsets of A. And that answer is, well, let's see. The empty set, of course, is a subset of A. And then the 3 singletons. The doubles. and then A itself. One, two, three, four, five, six, seven, 8 of them. Okay. So those are the 8 sets that are subsets of A. So this notation 2 to the A comes from the cardinality. Now, again, there's other notation. You also see like the power set of A, or you also see P of A and those sorts of things. But that's what that means. Okay. Now, this asks for the cardinality of that. And that number right there, the cardinality of that is 8. Okay. So how do we feel about 2, B, and C there? All right. So, yes. So there's a question about, is it with the size of 2 to the A? Yes, that is absolutely true. This right here equals... That is a very good question. So the question is this set right here equal to this? And the answer is yes. I mean, not the set. Is that number? Those two numbers are equal. Hence the notation. And we're going to see this again today. All right. This last one is just a tricky question, and it was kind of me hazing you a little bit. What is the size of the set containing the set A? And if you think of this, the easiest way to think of this is if you pull up a directory, right? So if I do this, if I pull up here this is my Ubuntu shell here. Let's make it bigger, right? If I go to my home folder, let's see, make dir set containing A. Oops, I can type. And I just made a directory called A, didn't I, too? Oops. Set containing and make director A. CD space A, and then ls again, and I'm going to put touch. What was in here? 0. Touch 1. Touch 2. So now I hit ls, and I have 3 items in here, right? A has 3 items in its directory, 1, 2, and 3. Okay? But if I go back up, and I ask what set containing has, and I hit ls, it only has 1 item. So it's not recursive, correct? The sets, are not, this cardinality thing is not recursive. So this is the number 1. Okay. So how do we feel about that one, 1 to 5 there? Oops. Oops, that's not working either. Forget it. How do we feel about that? This idea that this set here just contains A. All right? Now, A contains stuff, but, that's not what I asked. I just asked what was in A. There's a question here about recursive. Let's go back to what I mean by recursive. That's a good question. So the question is, what does recursion mean? If I do ls, I just get the stuff that's outside. But if I do, what is it, ls-r? Right, so if I do ls-r, it not only tells me what's in there, A, it then recursively tells me what's in all the subdirectories. So if I do ls-r, I get A is in, this dot here means the current directory. A single dot means the current directory. A double dot means the parent directory. And now it's telling me what's in A. So it's recursive. It'll actually go down, right? So if I do cd space, this thing's going to crash on me. I do this, and it tells me that has all that stuff. But my guess is that this is going to be very unpleasant. Oh, I guess not. Oh, because these are links. Never mind. So that tells me what's in all the directories. These things right here are symlinks. So recursive doesn't follow this. So that's what recursion means. Now, I'm asking for the cardinality. So in question D, I wasn't asking for the cardinality of A. I was asking for the cardinality of the set containing A. And it is not the case that this cardinality business is recursive. Okay. So I know this is a little confusing. I am thinking about A as 1, 2, 3, but then I'm asking again. I'm asking for, there's this, right? So now I have a directory. I have a set containing the set A. Okay. So that thing only has one item in it, even though A has 3 items in it. The set containing A only has A. Therefore, it's 1. All right. Which is, and don't, it's not, don't feel stupid about these things. It doesn't make, these things are tricky, especially if it's the first time you're seeing it and you're thinking about things like recursion for the first time ever. And it's confusing. What do you mean by that? And all these things. It's confusing. It's hard. So, don't feel like an idiot. It's obvious once you see it, but it's not until you see it. Math is hard. Okay. Let A equal AB and B equal BA. Does A equal B? And the answer to that is true, right? Because order does not matter in terms of sets. Okay, let A, and notice the angle brackets. This and let A equal list AB and B equal list BA or tuple BA, either one. It depends what you call. There's a whole bunch of names for these, and I'm going to go into that today. That's false, right? Because order matters. Let A be a set. Does that mean, is the empty set an element of every set? No. Okay. However, the empty set is a subset of every set. And the reason is that this last thing, right? Remember the definition of a subset. The definition of a subset is that every element in A is also an element of B. Okay? So, remember that elements and things are a little different. So, let's go back to the analogy that we had before about directories. Okay? If I create a new directory, and again, this is only an analogy because directories aren't determined by their contents. Directories have names. Sets don't. Sets are only identifiable by their contents. Directories are a little different. They can have names in computers. But, it's a broken analogy, but it works enough for this purpose as long as you're careful with it. So let's go back here to this thing. Where am I? Set containing. Okay. So let's get rid of A there. Okay, so now I'm going to make dir empty set. So there's the empty set, right? If I go in there, there's nothing in it, right? It's empty. Okay? Is everyone on board with that? That it's empty, right? This directory is empty. However, the directory above it is not empty. The directory above it contains an item, that empty set. Right? So this set here does not contain the empty set. It contains nothing. However, the directory above it contains the empty set. Okay? That's a weird thing. Okay? So that's about C. However, D, remember the definition of subset. For every item in A, and this is vacuous. All right? When A is the empty set, this is vacuously true because for every item in the empty set, there are none. For every item in the empty set, that item is also in B. Why is that true? Because there's nothing in it. So it's vacuously true. Everything that's in it is in the other set. Okay? So how do we feel about that? So I'm asking about 3, C, and D. How do we feel about that? That's one of these concepts that's going to kind of be in the back of our head about the difference between an element and a subset. Okay. And then, of course, name one thing you found memorable from the last lecture. I saw one of my favorites was Scott's mic setup. So you could have said one of the bad, jokes. That one was bad. I had a bad joke in there too, so one of those would have been fine. And all of this. If you're confused about that, please, by all means, we will talk. Now, the empty set, if you remember from the construction of the natural numbers, the empty set actually is a subset of every integer, of every positive integer. So for every number greater than 0, or integer greater than 0, not including 0, but greater than 0, it actually is an element of that number. But that's if you're using that's the technical thing about the construction of the natural numbers. There was also a discrepancy about whether or not n included 0. So it just depends. That was it's not that it depends. It's just how you define it. For our sake, it does, because computer scientists love to have it in there. If you ask a combinatorist, he's going to say no. If you ask a logician says yes, but we really call this omega. So it just depends who you ask. So for this class, the natural numbers include 0. Are there any other questions about that? I see we're back to talking about PHP. Okay. All right. Okay, so that's the quiz. If you have any more questions about the quiz, I know there was some confusion on that. I will be happy to talk to you about it in office hours. If you send me a DM in Discord, I'll be happy to talk about it some more. Um, but let's move on to this stuff because I was late today, and we're 30 minutes into class now. All right. So today we're interested in lists. We didn't get to lists last time, and lists have several names. They're called strings and stuff like that. And we're interested in subsets of a different distance of a size. So before we talked about the power set. So let's talk about subsets of a different size to begin with. And there's going to be more added to this outline when I go back and edit the video and stuff, because there may be more we get to. Hopefully there's more we get to. There might not be. Of course, the binomial theorem is going to be at the bottom here. So why do we care? Okay, so let's take some cards here. And we're going to take just a few cards. So let me pull up the cards. Let's see, card camera. There we go. So let's look at these cards here, okay? I've got, some cards, and we're going to take... My head is too big. There we go. All right, so we're going to look at these cards, and let's just take a few of them, right? So let's take 1, 2, 3, 4, 5 cards. Now, the question I have for you here, I've got 5 cards here. They're all distinguishable. So these 5 cards are a set, correct? There's the set of these 5 cards. 1, 2, 3, 4, 5. I need to move this way. Let's see. All right, so I've got these 5 cards here. Maybe the camera should go... Nah, just leave it. Okay, so I have these 5 cards here. Now, my question is, how many sets of size 2 can I form with these 5 cards? Okay, so I have the cards, and my question is... How many sets can I form? Okay. And some people are putting combinatorial numbers in there, and that's all nice. But let's just think about it again. Let's just think about it for here. So the 2 jacks, so we'll order these, although the order doesn't matter. Right? The 5 and the 6 are a pair. The 5 and the jack of clubs. The 5 and the jack of spades. The 5 and the king. Okay? So there's how many pairs? So if I match the 5 and the 6, the 5 and the jack of clubs, the 5 and the jack of spades, and the 5 and the king of clubs, that gets me 1, 2, 3, 4 pairs. So 5, 6, 5 jack clubs, 5 jack spades, 5 king. Now, anything involving the 5 has been counted. Right? So, So now there are four ways to pair the 5. All right. Now, I've counted that. So now I take the 6 and then I compare that with the jack clubs, the jack spades, and the king. I've already counted the 6-5 pair. There are 3 ways to pair these. Okay. Now, how many ways are there to count the jack of clubs? Well, I could pair that with the ones that I have not counted yet, right? Are jack spades, jack clubs with jack spades and king. Jack spades can be paired with the king. So there are 4 plus 3 plus 2 plus 1 ways to do this. Okay? Any questions about that? Okay. So, why do we care about this problem? All right? Well, let's go to a little script that I had to write one day. And here's the problem that we have. Camera only with, no, I want that one. All right. So here's a little script. Here's the problem I have. I have all of these peer leaders, undergraduate TAs, and they're only available during certain times. Okay? And we have to do trainings. And we're going to have 2 training sessions a week. So my question is, what times are best for the training sessions? And of course, this is in UTF-8, and this thing hates UTF-8. So I've got all of these options for the 2 training times. Because what I want to get everybody into one of 2 sessions. So I could do the Monday, my training times could be like at Monday at 8 a.m. and Monday at 9:15 a.m. Or, I could have all these other training sessions, such as Tuesday, those 2 times. I'm sorry, this is Thursday. So these are the training times. So the 1 and the 0s say when they can make it. So this person can make it on Wednesday. Let's see. I'm not explaining it well. Bugs Bunny can make the Monday 8 a.m. session. He can't make the 9:30. He can't make the 11. He could make the noon on Monday. He can't make it on Monday at 2 or Monday at 3, but he can make it there, and there, right? So Bugs Bunny can show up on Wednesday at 5. So if we had a training time, if one of our 2 training times included Wednesday at 5, Bugs Bunny would be covered. Okay? So we did a doodle poll, and we asked, okay, mark the times that you can attend. And Bugs Bunny, among those choices, said Wednesday at 2 and Wednesday at 5. Now, we're going to have 2 training times, and we want to see if there's a way for us to cover everybody with those 2 times. So I wrote a little script, okay? And the script goes over all of these columns in pairs. And the question is, how many times is the script going to run? How much looping is it going to do? So I want to check to see if I had the training times at this time and at this time, could Bugs be in one of them? So I wrote this little script, and I called it check times. And this is on my, I think the thing's on my desktop. Great. It's on my desktop, and my desktop's not there. Let's just do. What was I doing? This was, what was the name of the thing? Doodle Looney Tunes. And so what this script is going to do is it's going to loop. Okay? And the important thing to note here is that, let's say we had Thursday at 2 p.m. and Thursday at 3:30. Notice that there are 8 people that can't make it. Okay? So the question I have for you is, how many of these things are there? And the answer is that it's the exact same problem. All right? I'm taking all of the pairs of times, and I want to know how many different pairs there are. So that will tell me how many different things that the computer has to check. All right? I think everyone's still talking about PHP and not about this thing. Okay? And the answer is that that's the exact same problem. Okay? It is the exact same problem as the card problem. Okay? Now, here's the thing. What happens if I want to do every 3 times or every 4 times? Right? What happens if I'm okay with 3 training meetings or 4 training meetings? All right. Question. Just out of curiosity, how many of you are still on board with this and how many of you have checked out? So 1 to 5, give me your level of onboardness. Not boredness, your level of onboardness. Are you still on board with what I'm saying, or have I completely lost you? Okay. So I've got a nice little flat distribution of people here that are no longer on board. All right, so let's go back to poker then. I'm going to call this number so for this number, I'm going to call all right, so let's just rewrite this problem again. I'm going to use this notation to denote the 2 size subsets of A. And what are the 2 size subsets of A? I've got 3 items, and I want all the 2 size subsets. What are they? The 2 size subsets, they are AB, AC, and BC. And that's A choose 2. It's those 3 elements of that. Okay, now, 1 to 5. How are we feeling on this back on the train? Are we back on the train? Okay? This is the same thing as the cards. Before I had 5 cards, now I'm just doing 3. That's right? Okay. So, we're back on the train. Now, A choose 3 equals the 3-sized elements of the set. What is the 3-sized elements of the set? Right? What are the 3-sized subsets of A? The whole set, right? It's the set containing A, B, C. The set containing the set A, B, C. Right? It equals the set containing that. And by the way, what is the size of A choose 3? There's only one element in there, right? A itself. Okay. All right. Now, define the number in choose K as the size of A choose K, where the size of A equals N. Okay, now, 1 to 5, how do we feel about that? Okay, so this right here, A choose 2, I had 3 elements, okay? So from above, the size of A equals 3. So 3 choose 2 equals the size of A choose 2, which equaled 3. 3 choose 3 equals the size of A choose 3, which equaled 1. Okay? Now, this is a little different than statistics. You may have seen these combinatorial numbers before, but we're doing them differently. Instead of thinking of them as numbers, we're thinking of them as sets. Okay? We're thinking about A choose 3 as a set as the sets that the subsets that contain only 3 elements. We're thinking about the elements here as we're going to be the 3-size subsets. So let's go back to cards. Using this thing, let D be my deck of cards. A standard deck of 52 cards. All right. Is everyone on board with that? This is just a standard deck. It's got 52 elements in it. Okay? Now, D choose 5 is the set of all possible hands of 5-card poker. Okay? The 52 cards do not have a joker. It's 4 suits, 13 suits, and 13 cards in a suit. So, these 5 cards right here, okay? This would be a possible hand of poker. What is this? This is a pair of jacks, right? But this is a possible hand of poker. This is the same hand of poker. Order does not matter. This is a different hand of poker. Okay? So the set of all possible hands of poker is D choose 5. Okay? So D choose 5 equals so give me some elements of D choose 5 here, right? I've got the ace of hearts, the 2 of hearts, the 3 of hearts, the 4 of hearts, and it should be a big thing about this, the 5 of hearts, right? That's one set. Then I've got the ace of hearts, the 2 of hearts, the 3 of hearts, the 4 of hearts, and the 6 of hearts. That's another set. And so on and so on and so on. Right? And then at some point I wind up with the royal flush of spades. Is that all? So how do we feel about that? All right. So all the different possible hands of poker. Now, the size of D choose 5 is this number 52 choose 5. Instead of saying sets, I'm going to say collection. Why is it written like that? Well, that's because of the binomial theorem. All right. I'm going to go over it today, by the way, because I was a little late getting started. I'm sorry about that. If you're watching the video, of course, the video was cut to time, so I didn't hold you for extra. And since you could come back and watch the video later, I feel a little bad, but I don't, feel horrible, which is bad of me. But now let's go back up here. All right. The reason this is because of the binomial theorem. Okay. So what does the binomial theorem say? Okay. Does anyone remember what this thing says? The binomial theorem says x plus y to the n equals n choose 0, x to the 0, y to the n, plus n choose 1, x to the first, y to the n minus 1, plus n to n minus 1, x to the n minus 1, y to the first, plus n choose n, x to the 0, y to the n. All right, so example. If I want x plus y cubed, okay, that is going to equal 3 choose 0, x to the 0, y cubed, plus 3 choose 1, x to the 1, y squared, plus 3 choose 2, x squared, y to the first, plus 3 choose 3, x to the first, x to the 0, x to the x cubed, y to the 0. Now, how many, if I have 3 cards, how many 0-size subsets are there of this 3-card set? There's 1, right? The empty set. So this equals 1. How many 1-card subsets are there of these 3 cards? 1, 2, 3. Oops. Now, how many 2-card subsets are there? 1, 2, 3. How many 3-card subsets are there? 1, and, oh, that's it. So now, remember that x to the 0 equals 1, y to the 0 equals 1. I have the answer. It's y cubed plus plus 3 xy squared plus 3 x squared y plus x cubed. Okay, so how do we feel about that? How do we feel about that 1 to 5 using the binomial theorem? I'm less interested in the numbers. I'm very interested. What I want is the connection between this and this. Why is that so? What is the connection? Okay. Well, let's look at it. Okay. So let's do a little exercise here. If I was doing this, we'll use x plus 3 as just the way of thinking about this. X plus y cubed. X plus y cubed equals this. So this is x plus y cubed. Is everyone on board with that? That's what I'm doing. I'm taking x plus y and I'm cubing it. I'm multiplying it together 3 times. And over here, we're going to have, just over in this little corner here, we're going to keep in mind that this is actually, this generalizes. So I've got, for any positive integer n, I've actually got that x plus y to the end equals, and this is just off to the side, we're just going to kind of fill this in as we go, x plus y times x plus y times ... times x plus y, and there are a total of n terms. Okay? How do we feel about that, 1 to 5? Right? What am I doing when I'm cubing this term? I'm multiplying it 3 times. Okay? All right. That's kind of cool. Now, let's make these x's distinguishable. I'm going to call this xa. I'm going to call this one YA. I'm going to call this XB. I'm going to call this YB. And I'm going to call this XC. And I'm going to call this YC. So this is the A term, the B term, and the C term. All right? Now, I have 3 x's. The set of x's, right? I have 3 x's. I actually have we won't get into that joke. The set of x's, right? I'm going to call this big thing the x set. So the x set equals xa, xb, xc. All right? Now, how do I get the term x cubed when I multiply? Okay? When I multiply this out and I get the x cubed term, I multiply xa times xb times xc. Okay? When I multiply this out, when I FOIL, in order to get that term, right? I'm going to go whoop, 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 and I'm going to get x cubed. Plus this one, and that one to get x squared y. Plus this one, and this one to get x squared plus y. And then this one, this y with those 2 x's to get x squared plus y. I'm sorry, x squared times y. Okay? And that's not your glasses. That's because I'm using this pencil. And I'm doing that on purpose for a moment. That's kind of the aside. All right, I'm using the pencil marker. So I multiply XA, XB, and XC in order to get that. Well, how do I get the term x squared y? I multiplied XA, XB, YC, XA, YB, XC, YA, XB, and XC. How do we feel about that? 1 to 5. How I got x squared y. Okay. Are there any actual questions about this, by the way? Because let's see. Okay. Yeah, so you guys are going over the glitch. So when I multiplied these terms together, so how many ways were there to get 2 x's? How many ways are there to get 2 x's? There's 3, right? There's 3 ways to get 2 x's. In fact, there's 3. I'm sorry, how many ways to get 2 x's, right? There's x, choose 2. There's 3 choose 2 ways for me to pick 2 x's from the set x. How many ways to get xy squared? Well, same as how many ways to get 1x? And the answer there is 3 choose 1. How many ways are there to get y cubed? Well, how many ways are there to get 0 x's? Yeah, it will take forever to stop writing those as fractions. It took me 3 years. And that's the answer. And that's the connection. If I want to choose, if I look at this term, let's go back up here, right? I'm going to add together all these terms. And when I add these terms, that's going to become the binomial coefficient, right? I'm going to have 3 terms added together that are going to be x squared y, right? Because I'm going to have x squared y plus x squared y plus x squared y, 3, choose 2 times. Because that's the number of x's I have. There are three times when I make that multiplication out, I'm going to wind up there. Now, there are choose three ways to get the set x cubed y to the n minus 3. This meant that I chose 3 x's and all the rest were y's. The 2 came from me choosing 2 x's. Yeah, it'll be like when you get it. So you may have to stare at it a couple thousand times. Okay, but it's there. Okay. All right. So I got to the binomial theorem. Let's see. What did I not get to? So I talked about looping over subsets. That's that 2-thing size thing. And I haven't talked about the rule of and. I did talk about this. So I still didn't get to this. So what we covered today was mainly these functions, the choice functions, and their importance in terms of programming. Because we want to know when we loop these things, and I'll post these scripts to the notes. So I'll actually put them in the notes file so that you can see them. But what we want to do is when we run these scripts, we want to know how many times the script is going to run. Because if I'm choosing something huge, if my data set is huge, these numbers can blow up and be incredibly large. Now, we didn't get to the factorial and the following factorial today. Those have to do with lists. And we need that because what we want to do is figure out what this number is. So next time, we will talk to how to compute. And what I really want is not to compute, but to conceptualize. These, what are called combinatorial numbers, are binomials. And then we will get that and finally get to lists. Now, this thing about the binomial theorem is going to be with us for the entire semester. because it's extremely important because it stands at the center of number theory, the connection between number theory, combinatorics, counting sets, and counting loops. Okay? So the binomial theorem is going to be there, and it just kind of sits in between all of this stuff. So the major theorem of this class, in a sense, is this binomial theorem. And we're going to prove it this way. We're actually going to come back and prove it again when we do induction, because there's two ways to prove it. We actually proved this today, if you believe it or not. Wait, he did a proof and didn't tell us? This is actually a proof once you get it, right? A proof is nothing but a very convincing mathematical argument. Okay? And so this binomial theorem business, and I have to say this, you need to memorize it. Okay? You need to be able to do it right away. You need to be able to memorize this. But this binomial theorem and the proof for it, but especially the theorem itself, is going to be central to everything because it connects number theory to counting to all this other stuff. And so it's going to be huge, and we're going to use it when we do RSA, when we do Diffie-Hellman. It's stuck. Well, I don't know if Diffie-Hellman uses it indirectly. RSA uses it directly. So it's extremely important, and it's going to connect a whole bunch of pieces of this class. So we will finally get to lists next times, and we'll talk about how to compute these binomials. Yes, you're going to memorize. No, you don't need to memorize the proof. You need to memorize the theorem, okay? You need to understand the proof. The key here is understanding why this number is the same as this number. Why is it that the number of subsets is these binomial coefficients? That's the thing that's like big here. And then the other, but being able to use this binomial theorem is going to be very important because that's what we're going to use a lot of when we do number theory, because it's very important in the number theory stuff. Okay, I did go a little over. I'm sorry about the delay of getting started today. I'm going to try to get some stuff going. Reminder that you can watch this obviously over Twitch afterward, and then when I publish it to YouTube, I've still got to do the calc. I still got to do the calc quizzes from yesterday. By the way, if anyone knows how to use not Premiere Pro, After Effects, come talk to me. I need a little After Effects help. Anyway, that's it. I will talk to you again on tomorrow on Friday. Oh, reminder, tomorrow on Friday, I've got office hours on campus. They come after the PHP office hours. The PHP office hours are both online and in person. You get to pick. Tomorrow, I will announce where I am when I get there, find a spot, and get everything set up and make sure that the parking people don't kick me out. I will talk to everyone later.